Hello and welcome to the fourth of the lectures in this week 8 of the course titled Approximate Reasoning Using Fuzzy Set Theory, a course offered over the NPTEL platform. In this week, we have been discussing the interpolativity of fuzzy inference mechanisms. In particular, we are discussing the interpolativity of fuzzy relational inference schemes. We began by discussing the interpolativity of FRIs in the presence of a single input, single output rule. We saw that a couple of functional inequalities played a role in ensuring interpolativity. Of course, a single rule cannot capture the working of an entire system. We need multiple rules. So, of course, we need to discuss the interpolativity in the case of multiple SISO rules. The case of single SISO rule was only a stepping stone towards this, and towards our quest in exploring the interpolativity of an FRI in the presence of multiple SISO rules. In the last lecture, we have discussed the solvability of fuzzy relational equations. We have once again seen the important role played by the residuated lattice structure that is available to us if you relate a left continuous T-norm along to its residual implication. In this lecture, we will see how the solvability of fuzzy relational equations is indeed related and connected to the interpolativity of the underlying FRI mechanisms. We will also see an easy to ensure condition which will give us interpolativity, and we will see the role of Ruspini partition in this context. In the last lecture, we have seen that if you consider the underlying operations of either the sup-T or in-phi composition to come from a residuated lattice structure, that means the pair T norm T and the corresponding R implication IT, if they form a residual pair, essentially that means T is left continuous, then these are the results that we saw can be proven. If given Q and P, we want an R such that Q sup T composed with R is equal to P. This solution space is non-empty if and only if the relation which we denote by R hat or R cap, which is given as Q transpose in phi T composed with P, is not only an element of the space but also the maximal element of that solution space. Similarly, if you consider the solution space of the equation Q in phi T composed with R is equal to P, where Q and P are fixed and we are looking for an R, this space is non-empty if and only if the relation which we denote by R check, which is given as Q transpose sup T composed with P, is not only an element of this solution space. That means not only does it satisfy this solution, but it is also the minimal solution. It is also a minimal solution. There can be many other, but this is a minimal solution. That means there is nothing below this. Now, the question is, how is this related to interpolativity of an FRI? Specifically, CRI, which uses sup T composition, and BKS, which uses in-phi composition. Note that we are in this setting of residuated lattices. If T is left continuous, then we know on the unit interval this entire structure becomes a residuated lattice, and so we are considering FRIs where if F is given by T, then we are looking at the corresponding composition to come from either BKS with IT or CRI with T, and similarly if F is given by the corresponding residual IT, then once again one of these two compositions is what we are looking at. Of course, T is left continuous. Now, let's look at how interpolativity of FRIs is in fact ensured by solvability of these fuzzy relational equations. What do we have? We have this set of if-then rules, single input, single output rules, n of them, let's say, many of them. We are looking at the solvability of the equation Q sub T composed with R is equal to P, where Q and P are given. And we have seen that this has a solution only if R cap is a solution. Now what is Q for us? Q essentially is made up of antecedents AI and P is made up of consequence BI. So in the setting of interpolativity, the Q matrix is made up of the antecedents and the P matrix is made up of the consequence. And now we are looking for an R such that Q circle R is actually equal to P. Now, the essential question, the crucial question that we need to answer here is if R check is a solution of this system provided T and IT are actually assumed to be coming from the residuated lattice structure. Let's revisit one of the examples that we have seen already in previous lectures. Note here, the composition is sup min, and we know that minimum is a left continuous T-norm. In fact, it's a continuous T-norm, so it is a left continuous T-norm. And the corresponding R implication is the Gödel implication. So we have T to be min, and the I Gödel implication is given as follows. 1 if x is less than or equal to y, and y if x is greater than y. Now, the relations R1 and R2 are obtained from A1 and A1B1 and A2B2. Let's look at this. So A1 is 0.3, 1, 0.7 and B1 is 0.4, 0.8. We know that R1 of A1, B1 is obtained as, we write the transpose of A1 and use the Gödel implication 0.4, 0.8. So if I take 0.3 and 0.4, 0.3 is less than or equal to 0.4, so this is 1 here. 0.3 is less than or equal to 0.8, this is 1 here. 1 implies 1 is left neutral element of Gödel implication, so it is 0.4, 0.8. 0.7 is greater than 0.4, so this remains 0.4. 0.7 is smaller than 0.8, so this is 1. So this is how we have obtained the corresponding relation, and that is what you see here. Similarly, we have obtained the relation R2 using the Gödel implication and the antecedent A2 and the consequent B2. Now, what do we do next? We are in the realm of FATI. The inference strategy that we are using is first aggregate, then infer. So we are taking these two relations and aggregating them using min. So these two relations, aggregating them using min, it's a component-wise aggregation. So it is clear to see that this is the final relation we get. Now the question is it interpolative? Well, we have seen that if you compose A1 sup min composition, because we have fixed this as the minimum T-norm, with this relation R, we get 0.3, 0.7, which is not actually equal to B1. However, we have seen that with A2, we are getting the corresponding B2. But what we want is that for every input AI, we should get the corresponding and consequent BI. Now, in fact, if you look at this relation, what we have here is essentially R cap. Because what is it? What is R cap? R cap is Q composed by T of R. And what is Q? If you look at it, Q is actually A1, A2. P is B1, B2. So Q transpose is nothing but A1 transpose, A2 transpose, and we are using the Gödel implication here, B1 and B2 and min method. So essentially what we have here, what the relation that we have actually got as R is in fact R cap. Notice that is how we have got this, and we are taking the minimum component wise. So in essence what we are saying is not only is this R not a relation, but this R is in fact R cap, which means according to the solvability of FRIs, for this given system, if R cap is not a solution, clearly it is not going to be the maximal solution, and that means the solution space for this system is empty. That means given these antecedents and consequence, we will not be able to obtain an R such that this system is interpolative. A quick recap. So what we have is Q made up of antecedents, P made up of consequence, and we are looking at whether R cap is in fact a solution for the given system. Now, for min and girdle, we found that it is not interpolative. What if we change the T-norm and the corresponding residual implication? Would it work? Well, let's look at that. So let's look at taking another T-norm and the corresponding implication. For that, for the sup T composition, let's consider the Lukasiewicz T-norm, which is like this. This essentially we are taking the adding and then removing -1. So this is max of 0, x plus y minus 1. And for F, we are considering the corresponding residual implication, which is the Lukasiewicz implication. This is given as minimum of 1, 1 minus x plus y. So now, for the same A1, B1, this is the relation that we will get. Let's quickly work this out. 0.3, 1, 0.7, 0.4, 0.8. So now R1 is 0.3 implies 0.4. We know that Lukasiewicz implication has ordering property. 0.3 is less than or equal to 0.4, so that means this is 1. 0.3 less than 0.8, so this is 1. Now 1 is left neutral element, so it is 0.4, 0.8. 0.7 implies 0.4. When we put here 1 minus 0.7 plus 0.4, so it is 0.3 plus 0.4, so this will be 0.7. 0.7 and 0.8. 0.7 is less than or equal to 0.8, so this is 1. So this is essentially the relation R1 that we are going to get. And that's what we see. Similarly, we get R2. But this time we are wise. We know that this is in fact R cap itself, because we are considering the corresponding R implication. And in the case of Fati, what we would get is taking these two relations and then taking the min of it is in fact taking the Q transpose of it and taking the inf ILK composition with P, and the relation, if you actually take the component wise minimum of these two R1 and R2, this is what we get. So what are we trying to do? Keeping the same system but only changing the pair of operations from min and girdle to the Lukasiewicz T-norm and the Lukasiewicz implication. Is it interpolative? Let's look at it. So we have this R here, 0.3, 1, 0.7 composed with R. The R that we are going to consider is 0.91, 0.37 and 0.71. So note that the Lukasiewicz T-norm is max of 0, x plus y minus 1. So now when you look at this, what we have is 0.3 and 0.9. So add them up and remove 1. So it is max 0.2, 1, 0.3 is 0.3, 0.7 is 0.4. Same row with the second column, it's max of 0.3, 1. For any T-norm, 1 is an identity element, so it remains 0.3. 1, 0.7 is 0.7, and 0.7, 1 is also 0.7. So from here, if we get this, what we obtain is 0.4, 0.7, which clearly is not equal to B1. And that's what we have here. Now, with A1 not giving us B1, immediately it is clear it is not interpolative. If we do this for A2, of course, we seem to be getting the corresponding B2. So the point here is, even when we changed the pair TIT, we seem to be going nowhere. So now the question is, how is the solvability of FRIs really helping us in the interpolativity? To discuss this, let's go from existence of a solution to determination of the solution. We know that if R cap is a solution, then for the sup decomposition that we are considering, the solution space is non-empty. But the question now is, when will R cap be a solution? We tried different pairs, it didn't seem to work. But for this result to be useful, we need to know when R cap can be a solution. Note that Q consists of these antecedents, P consists of this consequence. So the question now comes down to when will R cap, which is given as Q transpose in phi t composed with P, be a solution for Q circle T R is equal to P. Well, the first such result on this was presented by Plavon way back in 2000, in which he said if the antecedents AIs are normal, that means there exists a point on the underlying space, the input space X, such that AA of X is 1 for every I, of course for different X perhaps with respect to AI. If the antecedents are normal and if this particular inequality is held. Now what does it say? When you take the supremum over X element of X, AI of X star AJ of X, for a pair of I comma J, this should be less than or equal to the quantity on the right hand side. Now what is this quantity on the right hand side? The infimum over the by implication applied for the corresponding membership values taken by Y on the consequence. What is this operation by implication? You may recall we have seen this. There is nothing but minimum of any implication, but in this case, since we are in the residuated lattice setting, it is minimum of X implies Y and Y implies X. Do recall that if you consider the T norm to be a minimum, we get the Gödel to be the corresponding R implication, and the by implication obtained for Gödel will look like this. If X is equal to Y, it is 1, otherwise it is min of XY. In the case of Lukasiewicz, we see that what we obtain is 1 minus mod X minus Y. You may recall this particular function as a relation, as an equivalence relation from the lectures on similarity classes. Well, so this is the first result that appeared, which said that if AIs are normal and if they satisfy this inequality for every pair of antecedents and the corresponding consequence Ij, then it will ensure interpolativity of the corresponding system. Now you would notice that we have tagged it as SP because this is also called the semi-partition inequality. We will perhaps have more, we will see this in more detail in the lectures to come. But this is the first such result that gave us a sufficiency condition to ensure interpolativity. However, you will see that this is not so easy to immediately determine while being very useful. Later on, almost a decade later, Stepnichka and others, they came up with a slightly modified result which said that if the antecedents are normal and also form a Ruspini partition, then we can ensure interpolativity. Now this is a very simple kind of a sufficiency condition. All we want are that the antecedents are normal and satisfy the Ruspini partition condition. Let's look at this example that we have considered before. If you look at A1 and A2, they are normal. However, they are not, in fact, they do not form a Ruspini partition. For instance, consider that X actually consists of X1, X2 and X3. So what we have is these 3 points. At this point, A1 is 0.3, 1 and 0.7. And if we consider A2, it is given as 0.4, 1 and 0.5. Clearly, these don't add up to 1. These add up more than 1, and definitely these two add up more than 1. So we consider these as X1, X2. So clearly, here the sufficiency conditions are not satisfied. So let's take an example where the sufficiency conditions are satisfied. So now what are we doing? We are taking the same 3 points, X1, X2, X3. Now A1 is given as follows. is 1, 0, 0.3, and A2 is 0, 1, and 0.7. So you see here, this is 1, this is 1, this is 1. So they add up to 1. We have not changed the consequence because the condition is only on the antecedents and not on the consequence. We consider the same system, that means sup-min composition, and the F used to relate the antecedents to the consequence to get the relation is the corresponding R implication of min, which is the Gödel implication. And let's look at R cap. So we know that what we need to do is actually take Q transpose, which is 1, 0, 0.3, 0, 1.7, use the Gödel implication with P, which is 0.4, 0.8, 0.3, 0.7. So now we can directly do calculation. Let's calculate this. We will take 1 against 0.4. Note that we are using an implication. 1 is the neutral element for Gödel implication. So it is 1, 0.4. Let's calculate this. So 1 implies 0.4 with minimum of 0 implies 0.3 is minimum of 0.4, 1, 1, 0 with 0.8, 0.7 is minimum of 1 implies 0.8 is 0.8, 0 implies 0.7 is 1. Now second row with this matrix here. So minimum of 0 implies 0.4 is 1, 1 implies 0.3 is 0.3, 0 implies 0.8 is 1 again, 1 implies 0.7 is 0.7 with respect to Gödel. Finally, minimum of 0.3 implies 0.4 is 1 because Gödel implication has the ordering property. 0.7 implies 0.3, when x is greater than y, it is y, so it is 0.3. Finally, 0.3 implies 0.8, again due to ordering property it is 1, and 0.7 implies 0.7 is 1. So this is the matrix that we get. So essentially the R cap that we are going to get is 0.4, 0.3, 0.3, 0.8, 0.7. We see that this is exactly the matrix that we have got. So in one shot, we have obtained R cap, which is essentially the relation that we would obtain if you aggregate the individual relations. The question is it interpolative? Now, according to the condition, we know that AIs, A1 and A2 are both normal and they form a Ruspini partition. Let's look at this. So to this R cap, we need to give A1. So A1 is 1, 0, 0.3. Note that sup Tm of R cap. So if you take this and then compose it with this matrix here, what you get is max of 1 and 0.4 is 0.4, 0 and 0.3 is 0, 0.3 and 0.3 is 0.3, and the second component 1 and 0.8 is 0.8, 0 and 0.7 is 0, 1 and 0.3 is 0.3. So when you take the max, it is essentially 0.4, 0.2, which is our B1. So when you see here, we have obtained for A1, when we compose it with this R cap, we actually obtained it is B1. A1 was the difficult antecedent, always we did not obtain the corresponding consequent. So we seem to have obtained a first success here. But let's also check for A2. In fact, if you check once again, we will see that we will get 0.3, 0.7, which is B2. So for this system, it seems to be interpolative. But what if we change the pair T and IT? Let's try that. Let's keep the AI same, but let us change the T norm to be the Łukasiewicz T norm, and of course the corresponding implication to be the Łukasiewicz implication. Now, once again, if we do the math, what we should get is in fact this matrix. So note that we are using essentially the Ukashevich implication here. And this is the R cap that you would get. Is it interpolative? Let's check. So that means we want to give A1 to this. So we have 1, 0, 0.3. Now remember, we have to use the Ukashevich T-norm, and R is given like this: 0.4, 0.3, 0.6, 0.8, 0.7, and then 1. So now it is max of 1 and 0.4 is 0.4, 0 and 0.3 is 0, 0.3 and 0.6. Now it's Ukashevich T-norm, which is max of 0, x plus y minus 1. If it is 0.3 and 0.6, it is 0.9, which is less than 1, so it is 0. And the second component will be 1 and 0.8 is max of 0.8, 0 and 0.7 is 0, 0.3 and 1 is 0.3. So the output that we get is 0.4, 0.8, which we see is in fact equal to B1. So once again, success with A1 and also success with A2. So we see here the condition, the sufficiency condition that we have, that the antecedents should be normal and form a Ruspini partition, seems to be sufficient no matter which pair of residual implication and the corresponding T-norm that we consider. So that in itself shows the reach and the potency of the sufficiency condition that we have got. Note that to ask for normality of antecedents is normally present even in practical applications, and all we want is the Ruspini partition. We know that typically we have a fuzzy covering, but if it also forms a Ruspini partition, then we are easily able to ensure interpolativity. Well, now this was the case with CRA when we use SUP-T composition. Now what about the corresponding Bks inference scheme? There we know that if R check is a solution, then the solution space where we use the in-phi composition is non-empty. Once again, we have the same question: when will this R check be a solution? Where Q and P are given as antecedents and are formed based on antecedents and consequence. This is the question that we have. Once again, the same sufficiency condition seems to hold. That means the antecedents should be normal and form a Ruspini partition. Is this really true? Let's check this out with one simple example. Note that we are considering the same set of rules. The antecedents and consequence are same. But now for the composition we are using Bks with Ukashevich implication, and so in this case the F becomes a corresponding Ukashevich T-norm. So now let's work out the math. Note here the R check. So now we are actually taking the transpose and using SUP star composition. So we have A1, which is 1, 0 and 0.3, A2, which is 0, 1.7, and we are going to use this with the corresponding B1, B2, which is 0.4, 0.8, 0.3, 0.7. Note that we take the Q transpose here, but we take P itself. So how do we get the relation R? We are going to apply max of the Ukashevich T-norm. So it is max of 1, 0 with 0.4, 0.3. So 1.4 is 0.4, 0.3 is 0, 1, 0 with 0.8, 0.7 is max of 1 and 0.8 is 0.8. Ukashevich T-norm applied on 0 and 0.7 is 0. Next, the second row versus the first column, it is max of 0, 0.3. The next component will be 0 and 0.8 is 0, 1 and 0.7 is 0.7. Finally, 0.3 and 0.4 is 0, 0.7 and 0.3 is exactly 1, which is again 0 with respect to the Ukashevich T-norm. Now 0.3, 0.7 with 0.8 and 0.7, we see that 0.3 plus 0.8 minus 1, which is 0.1. 0.7 is 1.4, minus 1 is 0.4. So this is the final R that we are going to get. Now that R check is now given as follows: 0.4, 0.3, 0, 0.8, 0.7, 0.4. So this is the R check we have got. Only question is it interpolative? Well, let us check once more. 1, 0 and 0.3. Note that we have to use the Bks implication here with R check. Now if you do this, remember this is the Bks inference. So that means we are looking at minimum of 1 implies 0.4, which is 0.4. 0 implies 0.3 is 1. 0.3 implies 0 is in fact 0.7 in the Bks implication. 1 implies 0.8 is 0.8. 0 implies 0.7 is 1. And 0.3 implies 0.4 is 1. So the output that we get is 0.4, 0.8, which clearly is B1. Similarly, if we give A2 as the input, we can easily check that we get B2 as the output. So it seems to work even for Bks. So it does not matter where the sufficiency conditions are applicable both for Bks and CRI when the T and IT are actually coming from residuated lattice. And it does not depend which T that we consider. So it is valid for any pair, any residual pair that we take. Well, what is it that we started with? We have this equation and we know that it has a solution only if either R cap or R check is a solution, where Q is made up of antecedence AI and P is made up of consequence BI. The question we asked was, if R cap or R check is not a solution for a given pair, does there exist another pair? We saw that we could not find. We were on a wild goose chase. So we modified the question and asked the question, how can we ensure that these two relations are indeed a solution for the corresponding fuzzy relational equation? Is there a simple condition that we can check? It so happened, yes, and that condition was simply that the antecedent should be normal and form a Ruspini partition. In this lecture, what we have seen is how the solutions of fuzzy relational equations involving SUP-T and INFI compositions lead to interpolativity of the corresponding FRIs, namely that of compositional rule of inference and the Bks inference. It's no exaggeration to say that the role of residuated lattices has only just started. In the weeks to follow, we will see that the rich structure and the myriad properties that residuated lattices have, they play an important role in ensuring a lot of desirable properties of fuzzy inference mechanisms. In the next lecture, we will discuss the interpolativity of similarity-based reasoning scheme. Let's point out some seminal works that have been done in this context. The first sufficiency condition was proposed by Frank Lavon in this paper way back in 2000. It was further modified later on in 2010 by Stepnichka and his co-authors in this work. Some related works also have to be pointed out by that of Perfilieva and Moskova. And this is also another paper or work dealing with solvability of fuzzy relational equations. As I said, we will meet in the next lecture to discuss interpolativity of similarity-based reasoning schemes. Glad that you could join us for this lecture. Hope to meet you soon in the next lecture. Thank you again.